In this video, we're going to start talking about one of the more important data structures in all of computer science, and that data structure is a graph. And honestly, graphs show up everywhere. So most introductory data science courses will spend a lot of time on things like arrays or linked lists, maybe stacks, queues, trees, hash tables, and all of those different data structures are important. But graphs are different. Graphs are much more general than the other data structures that I just talked about. A linked list is really just a restricted graph. A tree is really just a restricted graph. So a graph is a more general data structure that is sitting underneath of all of these ideas that you probably already know from data structures. And once you start noticing graphs, you'll realize that they're used to model many, many different applications like social networks and roads and GPS systems and communication networks, the internet, recommendation systems, scheduling problems, and honestly, a huge percentage of algorithms. So throughout the rest of this course, graphs are going to appear constantly. And because of that, we need to become very comfortable thinking about them mathematically. Another decorative transition slide, so we'll skip past this. All right, so let's start with a formal definition. An undirected graph is written as G equals VE, where V is a set of nodes or vertices, and E is a set of edges. The vertices represent objects, and the edges will represent relationships between those objects. So if two vertices are connected by an edge, that means that those two objects have some kind of relationship. Maybe they're friends in a social network, or maybe they're cities that are connected by a road. Maybe they're computers that are connected by a cable. Graphs are incredibly flexible because the interpretation depends entirely on the application. In an undirected graph, the edges have no direction. So if node U is connected to node V, then V is also connected to U. The relationship will go both ways. The graph parameters that we're going to constantly use are this. So we're going to say that N is the cardinality of your vertex set. It's just simply the number of vertices. And M is the cardinality of E, which is just the number of edges. So in the example on the slide, there are 8 vertices. So 1, 2, 3, 4, 5, 6, 7, 8 vertices. And there are 11 edges. So 1 edge, 2 edge, 3 edge, 4 edge, and so on and so on. One important thing to notice here is that graphs do not need to look like trees. They can contain cycles, they can branch in very weird ways, they can even be disconnected. So you could add on to this graph and say, well, here's 9 and 10 that are connected to each other. That's part of what makes graph algorithms very, very interesting. This slide is basically saying graphs are everywhere, and that's not an exaggeration. If you look carefully enough at many different problems, you'll find that a lot of them are going to reduce to objects that have relationships between them. And that's exactly what a graph models. So for example, let's think about communication. So in communication networks, maybe the vertices are the routers and the edges are the links between those routers. In, say, a transportation system, the vertices could be cities, and the edges could be roads or maybe flights that connect two cities. In the financial world, maybe vertices represent companies, and edges represent ownership relationships or transactions between those companies. In games, maybe vertices represent a game state, and the edges represent a legal move to move from one state to another. Even Google Maps is a graph problem, right? Your mapping software is just a graphing problem. Whenever you go to your car to travel somewhere, your GPS routing algorithm is basically solving something that we call the shortest path problem on enormous graphs that represent cities and roads. Your social network platforms are just giant graph problems. That's all that they are. Users are vertices, and friendships are, or maybe follows, are just edges in that graph. Recommendation systems are heavily graph-based. So graph algorithms are not this niche topic that you're going to see in an algorithms course. They're one of the central tools of algorithms. Now we need a way to actually store graphs inside of a computer. The first representation that we see here is something that we call an adjacency matrix. So suppose that the graph has n vertices. In the example here, there are 8 vertices. Then the adjacency matrix is just going to be an n by n matrix. So you'll notice here that we have 8 by 8. The entry A, or the matrix UV, is going to equal a 1 if there is an edge between U and V. And so you'll notice that here, that in the cell at 1, 2, there's a 1. So that represents the edge between 1 and 2. And you'll also notice that at the matrix at 2, 1, there's also a 1. So that also is representing the edge from 2 to 1 or from 1 to 2. But since it's an undirected graph, it doesn't matter. A 0 is going to represent the fact that there is no edge between the vertices. So here we have 1, 8, and you'll notice that node 1 and node 8 do not have an edge that directly connects them. So if you think about this in terms of like a social network, 1 is connected to 3, so maybe 1 and 3 are friends. 3 and 8 are connected to each other, so 3 and 8 might be friends, but 1 and 8 are not necessarily friends. So going back to the matrix, every possible pair of vertices gets a slot in the matrix. So 1, 2 is in the matrix, 1, 3 is in there, 1, 4, 1, 5, 1, 6, 1, 7, and 1, 8. Every single pair has a cell in the matrix. One really nice property of adjacency matrices is that the edge lookup is extremely fast. So if I ask, is there an edge between U and V, you can answer that in constant time. Because all you're doing is you're just looking it up in the matrix. You're saying, is there an edge between 6 and 5? And the answer is yes. Is there an edge between 6 and 2? Well, the answer is no. The downside to an adjacency matrix, though, is the space usage. A matrix is always going to require n squared space, even if that graph has very few edges. So if the graph is sparse, meaning that there's relatively few edges that are in the graph, then adjacency matrices are wasting a huge amount of memory. Another thing that's worth noticing here is that to scan all of the possible edges, we have to inspect the entire matrix. So if we want to know what are all of the edges in this graph, we have to look at the entire n by n matrix. So identifying every edge in the graph is going to take n squared time, even if there's only a small number of edges that actually exist. The second major representation of a graph is what we call an adjacency list. And in practice, this is often the representation that people prefer for what we call a sparse graph. So remember, a sparse graph is a graph that has very few edges. Instead of storing every possible edge, we're only going to store the edges that actually exist. So each vertex is going to store a list of its neighbors, and that's why it's called an adjacency list. So for example here, if vertex 3 is connected to vertices 1, 5, and 7, then the adjacency list for 3 is going to be 1, 5, and 7. Now it also contains 2 and 8, and so you'll notice 2 and 8 are there as well. So now the space usage for an adjacency list is going to be m plus n. And the reason that it's m plus n is because, well, there are n vertices, and there are m edges in the graph, and so our space usage is m plus n, which is different than n squared. And this is a dramatic improvement if we have a sparse graph. Now the trade-off here is that edge lookup becomes slower. If I want to know whether or not UV is an edge with an adjacency matrix, all I had to do was look it up in the matrix in constant time. But with an adjacency list, I have to scan through all of U's neighbors in order to determine whether or not U is connected to V. And so the runtime of this particular lookup is going to depend on the degree of U, which is what this is saying, is that checking the UV edge to see if it exists takes big O of the degree of U time. But identifying all of the edges in your graph becomes much faster. Now this is theta of m plus n, because we're only going to iterate through the edges that actually exist. So the big idea here is this, is that adjacency matrices are going to optimize fast edge lookup. If you need to look up whether or not an edge exists, you can do it very, very quickly by just simply looking it up in this two-dimensional table. Whereas adjacency lists are optimizing for space efficiency. So depending on what your algorithm needs, you can use one or the other. So different algorithms will prefer different representations. Now we start defining some of the more important graph terminology. A path is just a sequence of vertices where consecutive vertices are connected by edges. So if I say something like V1, V2, V3, etc., all the way up to VK, we're using edges in that graph, and then that sequence forms a path. So we could say that there's a path from 1 to 3 to 7 to 8. So V1 is 1, V2 is 3, V3 is 7, and V4 is 8. That is a path in our graph. Now, a path is called simple if no vertices are repeated. So here we have a simple path because we're going 1, 3, 3 to 7, and 7 to 8. We're never repeating a node or a vertex. The next important definition that we have here is what we call connectivity. Is the graph connected? So a graph is called connected if, for every pair of vertices in the graph, there exists a path between them. So if I only look at the left graph and I ignore 9, 10, 11, 12, and 13, if I only look at this subgraph is connected because for every pair of vertices, there exists a path between the two. So I can get from 1 to 5. I can get from 2 to 6. I can get from 8 to 4, and so on and so on. So in other words, every node can eventually reach every other node. If even one node is isolated or disconnected from the others, then we say that the graph is disconnected. So if we include these other vertices, and we include all of the nodes from 1 up to 13, this is not a connected graph. And the reason that it's not connected is there's no way to get from 1 to 13. So connectivity is an incredibly important property with graphs. A huge number of graph algorithms are going to answer questions like, can I get from one node to another? Basically, maybe the question is, can I drive from Chicago to Sydney, Australia? Well, not unless I get on a boat, right? So they are disconnected from each other. Is the graph fully connected? Which vertices are reachable from all other vertices? And these questions are going to show up constantly in things like networking and routing, even artificial intelligence, and some optimization problems. Some more graph terminology. So a cycle is a path that starts and ends at the same vertex. So for this particular graph, we might go from 1 to 2, from 2 to 4, from 4 to 5, from 5 to 3, and then 3 back to 1. So we're returning back to where we started. A cycle is called simple if all of the vertices are distinct, except for that first and last vertex, because those two have to match each other in order to complete the cycle. So cycles are extremely important in graph theory. Sometimes cycles are very, very useful, and sometimes they're actually quite dangerous, and they can break our algorithm if we have cycles. So for example, in networking, a cycle can create things like infinite routing loops. I go from server A to server B I'm sending data from server A to server B to server C, and then I send that data back to server A, and then I just keep doing that cycle over and over again. Well, I'm creating a routing loop. In, say, operating systems, cycles can create deadlocks. We don't want our CPU just doing the same part of a process over and over and over again. In a dependency management system, cycles can create these impossible dependency chains. So you could think of a dependency management thing being like prerequisites for taking courses. So if you say CS1 is a prerequisite for CS2, CS2 is a prerequisite for algorithms, and algorithms is a prerequisite for CS1. Well, then which course do you take first? Well, you can never take a course first because all of them have a prerequisite that you can't satisfy. But in other situations, cycles might be exactly what we want. Okay, so for example, in routing problems, like the traveling salesperson problem, we're literally trying to construct a cycle. Think about what the post office has to do every day. They have a driver that starts off at the post office, the central distribution center, takes all of the mail, travels to all of these addresses or packages or whatever they're delivering, travels to all these addresses, and then returns back to where they started. They started at the distribution center and they want to stop there. So that in that particular example, we do want a cycle. So a lot of graph algorithms involve one of the following things. They might involve detecting cycles, they might involve removing cycles, or they might involve constructing cycles. So knowing what a cycle is going to become very, very important. You hopefully already know what a tree is from data structures, but graphs will give us a very elegant definition of what a tree is. So a tree is simply a connected graph where you have no cycles. And that's it. That's what a tree is. So it's connected. It's acyclic, meaning there are no cycles. And these are the two properties that completely characterize what a tree is. So a tree is connected and there are no cycles. The theorem that we see on this slide is actually a very important theorem. So for any undirected graph on n vertices, any of the two that you pick will immediately imply the third. So the three statements that you have here are G is connected, so the graph is connected. The graph has no cycles, and the graph has exactly n minus 1 edges. So if you pick two of them, if you pick this one and this one, and you tell me that your graph has n minus 1 edges, and you tell me that your graph does not contain a cycle, then that immediately implies that your graph is connected. Now, if you pick two other ones and you say, well, what if it's connected and it contains n minus 1 edges? Well, if your graph is connected and it contains n minus 1 edges, well, that's going to immediately imply that you do not have a cycle. So this theorem appears constantly in graph theory, and after enough exposure, you'll start to notice it almost automatically. Rooted trees. So the last part of this little section here is talking about what we call a rooted tree. So a rooted tree is just a tree where we designate one of the vertices to be a root. Then every edge is viewed as kind of pointing away from that root. It's this regular parent-child relationship that you are familiar with when you were talking about trees in data structures. So when you define what the root is, now you give the tree a hierarchy. We can talk about things like parents and children and ancestors, descendants. We can talk about the depth. We can talk about leaves. We can talk about levels, heights, and so on and so on. All of the usual terminology that you learned in data structures. So the interesting thing is that the graph on the left, well, somewhat interesting, the graph on the left and the rooted tree on the right are actually the exact same structure. The only difference is how we're viewing it. Here we have a tree on the left, but if you look at this thing, this is hard to see as a tree. But once we define what the root is and we say, well, 1 is the root, well, when we make 1 the root, all of the neighbors of 1 are now its children. So 2, 5, and 7 are the children of 1. And then the grandchildren of 1 are going to be the children of 5, 2, 3, 5, 2, and 7. And so the children of 2 are 3 and 4, the children of 5 is 6, and the children of 7 is 8 and 9. So this is an important theme that we have in algorithms, is that sometimes just changing the perspective will change how understandable a problem becomes. And that will be a critical theme that we're going to see later on in this course when we start talking about other algorithm techniques like divide and conquer and dynamic programming and greedy algorithms. If we change how we view the problem, so instead of viewing it like this on the left-hand side, it may look like a disaster, and you'll say, I don't know what this thing is. But if we just change how we view it and we say, oh, well, the data actually looks like this. Oh, well, now it looks like a tree. And now it can become a much easier problem because we have a new perspective on the input. Excellent. In this next section, what we're going to do is we're going to start talking about graph connectivity a little bit more. And we'll talk more about we'll start talking about one of the more important graph traversal algorithms in all of computer science, and that's called the breadth-first search. And these ideas are going to show up everywhere. So the main question behind connectivity, which we already saw a few slides ago, but it's very simple. It's just simply, given two nodes in the graph, can one of them reach the other? And that sounds very simple when you think about it at a very high level, but the question appears constantly in many, many real applications that we've talked about already. So this is one of the fundamental algorithms for solving connectivity, is what we call breadth-first search. And the intuition behind breadth-first search is actually very natural. The idea is just going to be, you're going to start at some node, and you're going to explore outward from that node one layer at a time. So we'll see that algorithm very quickly. With breadth-first search, it's almost like we're dropping a pebble, in water, and we're watching that ripple kind of spread outward. Okay, so this is how breadth-first search is going to operate, and we're going to see that in a couple of minutes. So throughout the rest of this course, why am I talking up breadth-first search? The reason that I'm talking it up so much is that we're going to build on this algorithm, and we're going to build on many of these very core graph algorithms to build more advanced algorithms later on in this course. Okay, so the first problem that we're going to see or talk about here is what we call the ST connectivity problem. So with the ST connectivity problem, what we're given is we're given two nodes in a graph. So we're given a node S and we're given a node T, and I want to know, does there exist any path through this graph to get to T? Now this is different from the ST shortest path problem. With the ST shortest path problem, we're not just asking, does there exist any path in the graph from S to T? But rather what we're asking is this: what is the minimum number of edges, or in essence, the minimum cost, to get from S to T? And there are tons of real-world applications for this. This is not a difficult problem to motivate because they exist everywhere. So for example, let's think about, say, your favorite social network. So here I just threw LinkedIn on here. Suppose that I work at LinkedIn and I want some friend recommendations. So a reasonable idea might be something like this. Let's recommend people who are close to me in the graph, whatever close means. So maybe that means it's friends of my friends, or it's classmates of my classmates, or it's coworkers that are connected, through a few mutual people. All of these problems are shortest path problems. If people are friends of my friends, then those are probably good people to recommend because those are people that I probably know or that I have the best likelihood of knowing. But if there's a person that's 14 hops away from me, if it takes me 14 different jumps to get from me to another person, then there's a pretty good chance that I have no idea who that person is. So is that person going to be recommended to me? The answer is probably not, because I probably don't know who that person is. So graph connectivity is really about understanding, what can we reach? How does information flow in this particular network? And how close are different objects inside the network? So that's what this ST shortest problem is how close are objects in some graph? So let's start talking about it. Let's talk about breadth first search. The algorithm that we're going to see on this slide is one of the more important algorithms and graph algorithms that you're going to learn in this course. And it's what we call breadth first search. So BFS, or breadth first search, I'll use those terms interchangeably. The intuition behind it is very natural. You start at some node S, and you explore outward one layer at a time. So we're first going to explore all of the nodes that are one hop away from me, or one edge away from S. Then we're going to look at all the nodes that are two hops away, or two edges away from S, and then three edges away, and so on and so on. So it's just like this water and pebble example from before. It's like a wave spreading outward throughout the graph. You throw a pebble in a lake, and you see these ripples going through the water. Well, it's the exact same idea that's happening here. Wherever the rock hits, well, that's S, that's the start. And then as these waves make their way out, well, now I'm one hop away, now I'm two hops away, now I'm three hops away, and so on and so on. So the layers of breadth first search are going to work like this. L0 is going to contain the start node S. So L0 is always just going to be S. It's our starting node. L1 is going to contain all of the neighbors of S. So who are the nodes that are directly connected to S? Those are in layer L1. Layer L2 is going to contain the nodes that are adjacent to L1 that we have not already seen. So S does not exist in L2 because, well, we've already seen S. We've already been there. We visited it already. So in general, L of I plus 1 is going to contain all of the previously undiscovered nodes that are adjacent to some node in Li, but haven't yet been discovered. And that's where the really important theorem comes in. So the theorem that we have on the bottom here is, for every integer I, Li is going to consist of exactly the nodes that are distance I from S, or I should say it's going to consist of the nodes that are exactly I away from S. So not approximately, but exactly I away. And this fact is incredibly powerful because it means that breadth first search automatically computes the shortest path distance in an unweighted graph. So not only does it compute are things connected, but it's also going to compute the shortest path distance in an unweighted graph. So if there's a node T that first appears in layer L5, then we know that the shortest path from S to T uses exactly 5 edges. This slide is describing one of the key structural properties of breadth first search. So suppose that T is a breadth first search tree of some graph. And suppose that XY is some original edge in the graph. Okay, so we have a graph, and we have T being a breadth first search tree, and XY is an edge in that graph. The layers of X and Y can differ by at most one. So why does this make sense? Well, imagine that one endpoint was in layer 2. So you have maybe 7 that's in the L2 layer. So we have S that's in L0. We have a bunch of nodes that are in L1. Then we have 7 that's in L2. And then 7 is connected to something else. So let's say 7 was connected to, I don't know, 20. So 7 is connected to 20. Could this 20 be in layer 10? Well, the answer to that is no, because breadth first search is going to look at all of the neighbors of 7 and say, if we haven't yet visited 20, well, then it's going to end up in L3. So if there's an edge that's directly connecting them, they can only be one slot away. So if you had an endpoint in layer 2 and the other endpoint was in layers, let's say 10, well, that means there's an edge that's directly connecting them. But the node that's in layer 10 would actually have been reached much earlier. It would have been reached in, at most, L3. And maybe we had already reached it before. Maybe the 20 is in L1, or maybe it's in L2. But it's definitely not going to be any more than L3. So breadth first search would never allow that situation to happen, where 7 was in L2, and then the 20 was way down here in, say, L10. Breadth first search is going to explore the graph in strictly increasing order. Let's see, increasing order of distance from the start node. So neighboring vertices can only end up either on the same layer or one layer apart. Okay, so let's see an example here. In this example graph that we have on the screen here, let's say that node 1 is the start node. So node 1 is the start node. Who is in L1? What are the nodes that are one edge away from node 1? Well, it's just simply whoever's connected. So 2 and 3 end up in L1. They are nodes that are one hop away. It only takes one edge to get from 1 to 2, and one edge to get from 1 to 3. Now I look at the neighbors of 2 and 3. So who are the neighbors of 2 and 3? Well, we have 4, we have 5, we have 7, we have 8, and we also have 2 and 3, because 2 and 3 are neighbors of each other. But we're not going to add 2 and 3 to L2 because we've already visited them. So that's how breadth first search works. Since we've already visited them, the 4, 5, 7, and 8 are new nodes, so they get added to L2. But the 2 and the 3 are nodes that we've already visited before. Oh, and I forgot about 1. 1 is also a neighbor, because it's a neighbor of 2 and 3. But we're not going to add 1, surely, because we've already been there. And so 1 does not get added to L2, because it's already been discovered. So nodes 4, 5, 7, and 8 are 2 hops away. And then lastly, node 6 is 3 hops away. There's no way to get from 1 to 6 without traversing at least 3 edges. So breadth first search is going to give us a graph that has this very organized structure. And that's one of the reasons that breadth first search is so useful. It turns this kind of messy graph, the thing that we have up on top here, to what we see in the lower right corner. We have this nice hierarchy, something that's very layered and understandable. So let's do some simple analysis of breadth first search. The theorem that we have here is that breadth first search runs in big O of m plus n time if the graph was given by its adjacency representation, adjacency list representation. So the first thing that we're going to see here, the first proof, is a very straightforward, although it's a more weaker runtime analysis for breadth first search. And this is going to give us an n squared running time. So the idea is this. Breadth first search is building a collection of layers, L0, L1, L2, where each layer contains vertices that's a particular distance from the start node. Now, since every node can appear in one, or since every node can only appear in one layer, there can be at most n layers total. So since we have at most n layers, let's consider what happens when we process some node u. What we're going to do is we're going to scan through all of the edges that are incident to u. So all of the vertices that you can get to from u. In the absolute worst case, a node could be potentially connected to every other node in that graph. So the degree of u is at most n minus 1, which is big O of n. So for each incident edge, uv, we only spend a constant amount of time checking it. So we're only spending big O of 1 time processing that edge. And the amount of time, or the time that we're spending there, is trying to figure out whether or not v has already been discovered and whether it should be added to the next layer. So that can be done in constant time. So what do we have? What we have here is that there are at most n vertices, and each vertex may require up to n edge examinations. So therefore, the total runtime is bounded by n squared. Now, this is not the tightest analysis. The runtime that we actually get if we have an adjacency list representation is big O of m plus n. But the n squared proof is useful because it's simpler, it gives us a nice clean upper bound, and it sort of builds intuition as to where the actual runtime comes in. So just a quick summary of the top one. Each node occurs in at most one list, and we have a for loop that's running in n, at most n times. And when we're considering a node has at most n incident edges. So we have a for loop that's going through all of our vertices, and all of the vertices can be connected to, at most, all of the other vertices. Well, that ends up giving us n squared. But one of the nice things about breadth first search is that it's actually quite efficient. So as I said, if the graph is stored using an adjacency list representation, then breadth first search actually runs in m plus n time, where n is the number of vertices and m is the number of edges. So let's talk a little bit about where this runtime actually comes from. So the first thing is that every node gets discovered at most once. So the total amount of work involving the vertices is just n. So we're discovering every single node at most one time. The second thing that we have here is when we process a node U, what we're doing is we're scanning through the degree U. We're scanning through all of its neighbors. Well, how many neighbors does U have? Well, it's simply just the degree of U. That's how many neighbors it has. So the total amount of edge processing becomes this. It's for every vertex in your graph, sum up the degree of that particular vertex. And when you have an undirected graph, when you sum all these things up, you're going to end up with 2m. And the reason you end up with 2m is because when you have a node U connected to a node V, well, you have to process this node. And when you process this node, you're going to process this edge. You're also going to process this node. And when you process the node V, you're going to process this edge. So you're processing every edge twice. So this 2 is contributing to this. And m is just simply the number of vertices, the number of edges rather, that are in your graph. So the total runtime is, well, it's n plus 2m, which is essentially big O of n plus m. And this is one of the reasons that breadth first search is used constantly in practice. It's very simple, right? It's conceptually simple, and it's asymptotically efficient. Okay, now let's generalize the connectivity idea a little bit. Instead of asking, can S reach T, now we want to know which vertices are reachable from some particular node. So that collection of reachable nodes is what we call a connected component. So in the example that we see on the slide here, nodes 1 through 8 form one connected component, 9 and 10 form another connected component, and nodes 11, 12, and 13 form a third connected component. So the idea is this. Inside of a connected component, every node can reach every other node. But there are no edges that are connecting different components together. So this connected component and this connected component do not have any edges that are connecting them. So what you have is you have an edge that's essentially broken into these isolated regions. You can think of connected components like islands. You know, travel within an island. If you're driving from city to another island, well, that's entirely possible. I can get from node one, you know, city to city on an island with no problem. But travel to another island, if I want to drive from node 1 to node 13, is impossible, right? If I don't have a bridge, I can't drive from one island to another. All right, now I guess you technically could get to the other one by using a boat or swimming or something, but you can't take your vehicle. So your vehicle, unless it gets on the boat. Well, let's ignore that, because if you can get on the boat, well, then there'd be an edge between them, because there would be a way to get from the one island to another. So we're going to say boats don't exist. You can't get from 1 to 13 driving your vehicle. Here's a very practical application of graph traversal in this breadth-first search concept. Is what we call the flood fill operation. So this is the thing that happens when you open up some paint program and you click on that paint bucket tool where you want to, fill in everything that has the same color that's connected to that particular pixel. So suppose you click on some lime green pixel. So we're in this bird's head, I guess, and we click on one of these lime green pixels. The software that changes the entire connected blob of these lime green pixels into blue is the connected problem, the whether or not two vertices are connected to each other. So the graph interpretation that we have for this problem is this, is that every single pixel, so you'll notice that there's a small little pixel here, which is maybe what this is. And you have this pixel, which is what this is, and so on, and so on. Is going to define an edge. So these two things are going to be connected. They're connected, they are right next to each other, and they have the same color. So neighboring pixels are going to find what your edges are, and the blob then is your connected component. So there's an edge between them if they have the same color. So flood fill is basically just this. Start at one pixel and explore all of the reachable pixels of that same color. So the flood fill algorithm that you see on this particular slide is that we're just visualizing that flood fill idea. We're starting at some lime colored pixel and we're repeatedly visiting neighbors of the lime colored pixels. And eventually the entire connected region is going to get recolored. And notice something important that's happening here. We're not recoloring every lime pixel in this entire image. So it's not shown on this page here, but imagine if this were colored lime or this were colored lime. We're not going into the graph and saying change every lime color to be blue. We're only doing the ones that are connected to the starting location. And that's exactly what makes this a connected component problem. Once you start seeing graphs this way, you'll realize that graphs are hiding everywhere inside of all kinds of different applications. This slide is giving us a very high level reachability algorithm. So we're maintaining a set R, and that set R is going to contain all of the vertices that are currently known to be reachable from S. Okay, so we're still doing the connected component problem, but we're just seeing a nice pseudocode algorithm for how to do it. So initially, R is just going to be S. So R is our starting node, our starting vertex, because obviously S can reach itself. So then while there exists an edge, UV, where U is in R and V is not in R, we're simply going to add V into R, and we're going to keep repeating this process until there are no more nodes that can be added. So conceptually, this algorithm is extremely simple, but it's also quite important because it's really at the heart of what a graph traversal algorithm is that we keep expanding outward until no new vertices can be discovered. So breadth first search does this in this sort of layer ordering. Depth first search, which we will talk about eventually, we'll explore this in a very different style. So instead of expanding outward, like we're peeling the layers off of an onion, depth first search is a little more chaotic. It's just simply going to dive down as deep as it can on one path before backing up. And this difference between breadth first search and depth first search is going to turn out to make quite a bit of a difference. Okay, and we'll see what that is eventually. Not today, but we'll see depth first search at some point. In this next section, we're going to talk about what we call a bipartite graph. And so a bipartite graph is this. It's determining whether or not a graph is bipartite. Okay, so what does that mean? It turns out to be a surprisingly important graph structure. A lot of graph problems become a lot easier once the graph is a bipartite graph. So designing some algorithm for a graph problem when we're doing that, one of the first questions that we often ask is this, is does the graph happen to be a bipartite graph? Because if the answer is yes, we're going to be able to use a much faster and much cleaner algorithm for solving that problem. And that's what's really interesting about bipartiteness is that it's deeply connected to graph traversal, which is why we're talking about it in this set of notes. So in particular, breadth first search is going to help us test whether or not a graph is bipartite. So we're going to combine several ideas that we've seen now. We're going to talk about graph coloring a little bit. We're going to talk about graph layers, which we saw with the breadth first search. We're going to talk about breadth first search, and then we're going to talk about cycles. We started that a little while ago. Now we're going to get back into it. All of these ideas are going to fit together very nicely in this idea we call graph bipartiteness. An undirected graph, G, is called bipartite if the nodes can be divided into two groups. In this slide, they're colored blue and white, but it doesn't really matter what we color them, such that every edge connects a blue node to a white node. Another way to think about this or another way to think about it is this, is that no edge is allowed to connect two nodes of the same color. And this shows up constantly in applications where there's kind of naturally two different types of objects. So for example, think about the stable matching problem that we saw in a previous video. We might have students that are on one side, our med school students on one side, and hospitals on the other. In scheduling, we may have jobs on one side and machines on the other. In a networking problem, we might have users on one side and servers on the other. We're connecting users to servers. We're connecting jobs to machines. We're connecting students to hospitals. Edges are only going to go between those two groups. This is a very natural definition that we have for many problems. So consider stable matching. It doesn't make a lot of sense to add an edge between two hospitals because what does that even mean for two hospitals to be connected? Or what does it mean for two med students to be connected? I mean, maybe it means that they're friends, but in the terms of stable matching, who cares, right? The only thing that we care about is whether or not a student gets paired up with a hospital. So the graph that's shown on this slide is bipartite because every single edge has one vertex that's colored blue and one vertex that's colored white. So I'll just highlight a couple of these edges. One of them is blue, one of them is white. One of them is blue, one of them is white. One of them is blue, one of them is white. There are no violations of this anywhere in the graph. And if there are no violations, then you have a bipartite graph. So why do we care? Okay, why do we care about bipartite graphs? The reason that we care about that is many, many graph problems are going to be difficult in general. We're going to see a handful of these throughout this semester where we have this really, really hard graph problem, but it's going to be much easier if the underlying graph is a bipartite graph. So for example, stable matching, it worked very nicely because the graph naturally split into two groups. You had hospitals on one side and med students on the other side. We ended up with this nice polynomial time algorithm, this n squared algorithm. There are going to be optimization problems that we're going to see later in the semester, and we've already seen already, like the independent set problem, where the bipartite version is dramatically easier than the general version of the problem. So think about what an algorithm might be for finding the largest independent set. Right? If you go back to the running time analysis video, we talked about independent set being an exponential time algorithm. If you're trying to find the largest independent set. So what would the algorithm be if your graph was a bipartite graph? So if your graph is a bipartite graph, how do you find the largest independent set? Well, it turns out you can do that in polynomial time, and it's a fairly easy algorithm. So recognizing the structure of your graph is going to be incredibly important in algorithm design. Sometimes the hard part is not actually solving the problem. The hard part might be just recognizing, oh, this is a graph that has this special structure that I can exploit. So the example graph that you see on the left here is a bipartite graph. But again, how we're viewing it, it doesn't look like a bipartite graph because visually it's just messy. The nodes are scattered around, the structure is very hard to see. If I were to give you the node on the left, it wouldn't be obvious that this is a bipartite graph. But if I redraw the graph like you see on the right, you can look at this graph and say, oh, this is absolutely a bipartite graph because the nodes have been separated cleanly. We have blue nodes and we have white nodes. So suddenly the bipartite structure becomes obvious. And this happens a lot in graph theory, is that the same graph can look confusing or very simple depending on how you draw it. What we see on this slide is one of the most important lemmas that we have about bipartite graphs. If a graph is bipartite, then it cannot contain an odd length cycle. And this gives us a very powerful way to recognize whether or not a graph is bipartite. Okay, so why is this true? If a graph is bipartite, it cannot contain an odd length cycle. So suppose we start walking around a cycle and we alternate colors. So let's say the first node is blue. So I'm gonna start right here. Here's node number, I don't know, node number 0. Node number 0 is blue. The next node that we walk to has to be white. So I'm gonna walk here. This is node number 1. The next node that we walk to has to be blue. That's node number 2. The next node that we walk to has to be white. That's node number 3, and so on and so on. So we alternate blue, white, blue, white, and so on and so on. If the cycle has an even length, then everything is going to work out perfectly. So let's look at this graph that we have on the left. I have a cycle going from here to here, so there's 2 nodes, here's 3 nodes, here's 4 nodes, and then we're back to the start. So this one has a 4 node cycle. Everything worked out perfectly. But let's take a look at the one on the right. This one has a 1, 2, 3, 4, 5, and then back to where we started. So this is a 5 length cycle. Now let's see what happens here. Well, let's say we start at this one, color it blue. And then I color the one next to it white. And then I color the next one, the next node on the path blue. And then I color the next node white. Then I have to color the next node blue because that's how you would have to color this in order to maintain bipartiteness. But then I'm connected back to the original, which means, uh-oh, I have 2 blues that are connected. So eventually, if you have an odd length cycle, this is going to happen. Something is going to break. Eventually, we're going to return back to that starting node, and we're going to be forced to give it an opposite color from what it already has. But that's impossible. So odd cycles and bipartite colorings fundamentally contradict each other. You can't have an odd cycle and a bipartite coloring. That just doesn't exist. So this lemma that we have here is incredibly useful because detecting odd cycles is often easier than trying to directly construct a coloring. So graph coloring is not something we've talked about in this course yet. We will in a future video and near the end of the semester. But graph coloring is not easy. It is not an easy thing to do. But detecting an odd length cycle, well, that thing actually is quite easy to do. Now we're going to connect bipartiteness back to breadth first search. Okay, so how do these two things relate to each other? Suppose that we run breadth first search, starting from some node S. So here's our starting node S, and we're producing different layers. So we have layer L0 at the start, and then we have layer L1, L2, L3, dot, 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 all the way up to some LK. Exactly one of the following must happen. So either no edge is joining 2 nodes in the same layer. So in this one example that we see on the left, there are no nodes in the same layer that are connected to each other. If that happens, the graph is bipartite. So if no edge is connecting 2 nodes in the same layer, we know that the graph is bipartite. Or the second thing happens, and the second thing is this, is that there does exist some edge that joins two nodes in the same layer. And in that case, what we have is a graph that contains an odd cycle, and therefore it's not bipartite. Okay, so this is the second thing that could happen. An edge of G could join two nodes in the same layer, and so therefore G has to contain an odd length cycle, and if it has an odd length cycle, it is not bipartite. So breadth first search layers are kind of secretly giving us this coloring. Maybe even layers can be one color and odd layers can be another color. So maybe everything from 0 and 2, these are our blue nodes, and everything at 1 and 3 and everything that's odd can be our white nodes. On the left, this works fine. On the right, not so fine. We have two nodes in the same layer that are connected to each other. They are the same color, and therefore the graph cannot be bipartite. So this is one of those moments in algorithms where you have all of these different ideas that seem disjoint from each other that actually connect together very elegantly. Okay, so let's see why this is the case. You may be looking at 1 and 2 and saying, sure, maybe that's true, but I don't know why it's true. I don't believe, or maybe you don't believe me. Maybe you're like, nah, that can't be true. There has to be a third way to do this. Maybe there's another way to do this. What we're going to see in the next couple of slides now is going to be proofs of this. Why is it only one or the other? Well, hopefully you see why it has to be one or the other. It's making very general claims here. So it's either saying no two nodes in a layer are connected, or there are two nodes in a layer that are connected. So hopefully you look at that and say, oh, okay, I get it. I see why it has to be one of these two, because either nothing is there or there's at least one thing there. And that's it, right? That's all this is saying. So now why does one give us a bipartite graph and why does the other ensure that a bipartite graph does not exist? So let's prove the first part. The first part is this. Suppose that no two edges join no two nodes in the same breadth first search layer. Okay, so no edge of G joins no two nodes in the same layer. If that happens, then that means the graph is bipartite. So what is the proof? So remember the breadth first search property. Every edge connects nodes whose layers differ by at most one. Since edges cannot stay within the same layer, then that means every edge must connect to adjacent layers. So the original thing that we're assuming here is that no edge joins two nodes of the same layer. Well, if no edge can join two edges or two nodes in the same layer, then the only thing that a node can be connected to is an adjacent layer. So I can only be, if I'm in node, or if I'm in layer 2, I can only connect to nodes in layer 1 and layer 3. I can't connect to another one in layer like 7. That's something that we saw a few slides ago, is that we can only connect to a layer that is one away from each other. Well, if there's only nodes that are one away from me, then the way that we color them is immediately giving us a bipartite coloring. So for example, all of the even ones are blue, and 4 would be blue, and 6 would be blue, so I got blue, blue, and so on and so on. All of the odd-numbered layers are going to be white. So this is white, 5 here is going to be white, 7 is going to be white, and so on and so on. Since every edge is going between adjacent layers, every edge is automatically connecting to an opposite color. Blue is connected to white. White is connected to blue. Blue is connected to white, and so on and so on. So this is producing a valid bipartite coloring. And since we have a valid bipartite coloring, the graph is bipartite. So the proof of one here is generally not too complicated. I find that most people understand this one without too much difficulty. The more difficult one now is going to be the second part. Why is this true? So why do we have this where an edge of G joins two nodes of the same layer if an edge joins two nodes of the same layer, then the graph has to contain an odd length cycle. So let's prove that. We'll prove the second part. Suppose that there exists an edge connecting two nodes x and y in the same layer. So I have two nodes here that are connected by an edge, and they are at some layer Lj. All right, maybe it's layer 12. I don't know. It doesn't matter what layer it is. Lj. Let's say that z is the lowest common ancestor of x and y in that breadth first search tree. Okay, so the lowest common ancestor, you make your way, x has a neighbor and y has a neighbor, and that's in layer Lj minus 1. Both of those had neighbors, to Lj minus 2, and then Lj minus 3, and so on and so on. Eventually, there's going to be a node that's the same for both of them in some layer Li, where I is less than j. Because eventually you're going to get back to the root. Eventually you're going to get back to S. So if you get back to S, well then I is just simply 0. It is S. It is the root node of this tree. Well, let's assume this in general. Let's suppose that we have this node Z that's the lowest common ancestor in layer I. So what we're going to look at is, look at this cycle. So look at this cycle that goes from Z to X, from X to Y, and from Y back up to Z. What is the length of this cycle? Well, what do we have? We have 1. We have an edge from X to Y because that was our assumption. Our assumption here was that we have two nodes in the same layer that are connected to each other with an edge. So the number of edges that we have there is, well, just 1. What is the length of the path from Y up to Z? Well, if this is at layer J and this is at layer I, then the path length is just going to be J minus I. If you want to see this in a little more concrete, imagine something's at layer 2. So we have maybe a 7 at layer 2, and we're connected to maybe a 6 in layer 3, and we're connected to a 4 in layer 4, and we're connected to a 12 in layer 5. What is the path length from 12 back to 7? Well, 1, 2, 3, which is just simply 5 minus 2. So the path length from Y up to Z is J minus I. Well, what is the path length from Z down to X? Well, it's the same thing. It's just J minus I. Because it's the same going from layer Lj to layer Li. So therefore, the length of that path is also J minus I. So the total length becomes 1 plus J minus I plus J minus I. Well, that's just simply 1 plus 2 times J minus I. Well, that's just 1 plus 2 times some integer k. Well, that's an odd number. And the reason that it's an odd number is it's 1 plus an even number, because 2 times k is an even number. So since 2k is an even number, when you add 1 to it, you get an odd number. So what do we have here? What we have is we have a cycle that is odd. So we have this odd length cycle. Because of that, the graph cannot be bipartite, which is what we saw a few slides ago. So this is a really nice application of all of the things that we've seen so far up to this point in the video, is we're using the fact that we have this odd length cycle to show that our graph cannot be bipartite. So we're using breadth first search, we're using cycles, we're using odd length cycles, and that will tell us that if an edge joins two nodes of the same layer in a breadth first search, then the graph has an odd length cycle and therefore cannot be bipartite. So the corollary to this this lemma theorem we saw on the previous page is this, is that we can combine everything together into this really nice corollary here, which says that a graph is bipartite if and only if it contains no odd length cycle. And that phrase if and only if means it's true in both directions. So if the graph is bipartite, then it cannot contain an odd length cycle. And you can say it backwards as well. If the graph contains no odd length cycle, then it must be bipartite. So odd length cycles are exactly the obstruction to bipartiteness. Nothing else can go wrong. And algorithmically, that is fantastic because it means that we can test whether or not a graph is bipartite simply by running breadth first search and checking whether or not some edge connects two nodes in the same layer. So what initially looked like this really challenging graph coloring problem actually turned out to be a graph traversal problem. And as I've said before, this is one of the recurring themes in this course, is that problems that look completely different on the surface often often turn out to be very, very connected once you look underneath the hood to see what's actually going on.